Okay, I did a few sort of tests before I thought I'd sort of go through and check the general alignment of the tuner, see what it's like. And I set my red and short signal generator to sort of 1500 kilohertz and went to 1500 kilohertz on the dial, which is here. Tuned around, couldn't find anything. Tuned all the way through, couldn't find anything. I think what's going on? I mean, it can't be that far out of alignment, so I tuned to mid-scale about 800 kilohertz and found 800. I was like, okay, that's central, so why can't I find 1500? Okay. Then I tuned to 1 meg, which is here, and tuned up and down, couldn't find anything. Tuned back down here, and it was around here. I'm thinking, huh? So I retuned again, and I tried something like 1200 kilohertz, 1.2 meg. Came up, nothing. It was right down here, even further down. And I'm thinking, well, what the hell's going on? And then I realised that when I got the tuner, the string had been disconnected, and when I reconnected it in the obvious way, the obvious way was the wrong way, and when I was tuning up in frequency, increasing the frequency, I was actually increasing the capacitance and actually slowing the tuner down. So the problem was that the tuning wheel was around the wrong way. So I spent an hour last night farting around with the tuning dial, trying to get that in the right place, and finally managed to get it strung up. And let me just show you, just turn the radio around so you can see. It's a good view. So here's the tuning dial, and what I had was the string coming up here and coming to this pulley here, going along to the left hand side here, and then down to the tuning control, and then back up. So basically, even though when I turned the tuning dial clockwise, the needle moved clockwise, the tuning capacitor was actually going in the incorrect direction. That's been fixed, so we just want to check the alignment now. There's one other thing that I'm a little bit confused about, and I'm going to have to check the manual on this. These two Plessey trimming capacitors are actually, I think they're called beehives. Yeah, they're beehive trimming capacitors. That's I think the trade name they use. This one here is floating in the air. I'm not sure where it's supposed to go. I think it's supposed to solder to chassis, and it looks like either the local oscillator trimmer or the aerial trimmer. I'm not sure which capacitor this is. You got the bottom one will be either local oscillator, RF, and antenna tuning. So it's a 3-stage tuning gang. So what I've got to do is to ascertain what tuning capacitor that is, but I'm pretty sure that's got to be soldered to a 0-volt connection or a ground connection, which that's easy enough to do. This one here is fine, it's in place, and that's all okay. So I think what we'll do now is we'll just quickly check to see what our RF alignment is. I don't really expect the IF to be that far out. I've got a feeling this tuner, as I said earlier, I don't think this tuner's ever been used. I could be wrong, it could have been used, but all the capacitors, all the valves look clean. It all looks in pretty nice condition. So what I'm going to do, I'm going to go through, I'm kind of going to get it so you can see, I don't know if you can see, yeah, so we're interested in the Broden Schwartz's frequency counter here, and I'm going to hopefully show you, we're looking at the bottom scale, and we're just going to do a couple of checks on RF section, just to see what the RF, if the RF is actually a long way out or not. So I think we'll start at 550 kilohertz now that the tuning capacitor is actually in the right direction. So it's 550 kilohertz. Okay, so we'll turn the volume up, and we can't hear anything. And I'm going to tune on the Roden Schwartz to 550 kilohertz. Coming up now. Well, there's your IF, and then you should get another one here. There it is. Oh, okay. That's pretty good. So, yeah, that's about right. 550 kilohertz. Quite happy with that. So let's go to 700 kilohertz. So tune to 700 kilohertz. Watching Roden Schwartz again. Okay, we're a little bit out there. You'll also notice the magic eye. Okay, so there's a slight shift there, slight unlinearity there. Let's turn the volume down a bit. Let's go to 1 meg. into 1 meg. Okay, we're slightly out, but it's not too bad. It's staying fairly linear. It's 974 kilohertz. Oh, that's volume. And then let's go to 1400 kilohertz. Tune to 1400 kilohertz, 1.4 meg. Okay, so there is a slight scale linearity problem there, and that will be one of the first things to check to see if we can improve on that. Obviously there's the IF alignment, but at the moment, because the performance of the tuner is actually very good, apart from the scale calibration is obviously wrong, I'm not too worried about the IF. I've got pretty sure that the IF is pretty well aligned, and I don't want to check that at the moment. I'm going to resolder that tuning capacitor, and then we'll come back and see if that improves our RF alignment. Right, I'm going to have a go at resoldering this beehive back on. Let's see if you can zoom in a bit so you can see a bit clearer. This connection needs to go to the chassis, which is bar here. For those who are watching and thinking, oh my god, he's working on it live. It's not live. Well, it is live, I suppose. It's all that is I've got the heater currents keeping the valves on. The high tension is turned off, so there's no risk of anything at all. So I'm going to try and resolder this on, see if we can get a good connection. Got the iron at maximum heat. Try and do it so you can see what's going on. Cool, they get pretty hot pretty quick. There you go. How about that? Is that good? Is that on there? No, that's crap joint. So what I'm going to do is I'm going to scrape that back. Let's get a knife and just scrape back any verdigris. Let's give it another go. The trouble is with the soldering iron is getting the heat into sort of metal parts like this, so what you really need to do is get the heat the metal part up first. Heat the part up that's got the most thermal mass, which is this bar here. So let's get some heat, try and get some heat onto that. Sometimes here you need a sort of like a bigger iron really. But I'm going to try it with this iron first. It's starting to warm up now. The other thing you can do is apply a load of flux to it. See what that's like. It's on there at the moment, so that looks fairly solid. So I think the next thing to do is we'll just check, see if it's pulled our RF alignment in any further. Now, what usually happens with these trimming capacitors is, or tuning capacitors, you've got 3 gangs here. There's one that will match the aerial, incoming aerial, keep the aerial matched depending on what frequency you're on. The other one does the local oscillator, and the third one usually does the RF amplifier. Most sort of domestic tuners won't have the third gang, they'll only have the 2. The slightly unusual thing about this radio is that, if you can see here, these gang here and this gang there, they're usually assigned for VHF only, FM. And it looks like they're actually using that for some reason. I'm not sure what it is. It might be for band spread, something like that, because this tuner has band spread. I'm not entirely sure, but I've never seen that used in a medium wave or AM radio. It's always been in a VHF radio with AM. If you've got an AM and FM radio, you usually have both of these. If you've got FM radio, you only have those, and AM radio, you usually have just the final tuning gang. So let's run it through again, have a listen, see if it's any better aligned, and if not, we'll start to get the screwdriver inside it. Right, we're doing a quick check just to see what the IF alignment's like. That's the intermediate frequency. It's not going to be easy to adjust on this tuner because it's been sealed with wax, so therefore you can't get to the cores, and that's a good thing. It means that someone hasn't been in there, someone like me, to tinker around and adjust the cores. So what we're going to do is we're going to keep an eye on this Magic Eye signal. Roden Schwartz is going to sweep the IF frequency. Now the peak should be at 470 kilohertz. What we're going to do is look for the peak on the Magic Eye and see what our IF frequency is. Now if it's within a sort of like 5 kilohertz or so, that's fine. I'm not going to unmelt the wax just to align that. That should be fine. I'm going to tune, watch the frequency counter here, watch the Magic Eye. When that's peaked, that will be our IF frequency. We're on narrow bandwidth. You can't see that's out of scale. I've zoomed in so you can see the meter easily, and you can see the Magic Eye at the same time. So I'm going to sweep through on the fine scale, and you can hear the signal coming through. And watch the signal meter here. You see it closing. Peaked about there. Going back again. So my IF is at 467.5 kilohertz. The spec is 470 kilohertz. At the end of the day, that really isn't that super critical. As long as it's within the ballpark, the receiver will work perfectly well. It's not that critical. If it was at 475, 480, 485, yes, I would be a bit more concerned, and I'd have to bring it in. Right, I think the first port of call with this tuner before we get into alignment is to replace these capacitors. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I think 0.1 microfarad capacitors. I've got some, I think I've got 10 0.1 microfarad capacitors. Now these Hunt capacitors often fail leaky, and if they do that, you're always going to have problems with biasing on valves and grid biasing being out of line, sort of thing, causing valves to overheat and overconduct and burn the valves out eventually. So you can hear the tuner is actually on at the moment. Let me just demonstrate why I think some of them are failing. Then I think what I might do is just disconnect one and do a high voltage check on it with the isolation tester, which is my preferred way of checking these things. So if we look at the pharmacia, we're seeing we're drawing 8 milliamps at 62 volts. So this increases to a sensible voltage. I reckon 250 volts is good. That's probably roughly what it will run at. We've got 40 milliamps drawing, okay? So in theory, if I turned the heaters off and the valve stopped conducting, I should see, in my mind, 0 current passing, unless there's any resistors across the supply. So I'm taking the heaters off now. So there's just, the reason why you can still hear it is the amplifier, the valves are still working on their sort of latent heat. Audio's dropping away. There we go, the valves are cooled down, they're not emitting anymore. But we've still got 18, 17 milliamps, 15, it's dropping back. But there is still some power consumption there. Now, I'm not sure if that is a leaky capacitor or not, but I think we need to maybe disconnect a couple of these capacitors, check them out, see if we have indeed got some leaky capacitors, because these Hunt's capacitors are unreliable, and they probably haven't been used as well. I don't know if that's detrimental to them or it's better if they're used more regularly, but I know most people say that these Hunt's capacitors need to go, and who am I to disagree? So let's get some of these caps out and see what they're like. I've disconnected one of these Hunt's capacitors just to see how leaky it is. So we connected it up to an isolation tester, or better known as a Mega maybe in the UK, And what this meter does, for those who don't know, is it applies a high voltage across the terminals, or a voltage that you specify, and it tells you the resistance of the component that's across it. And it's designed for testing for isolation faults on equipment, basically safety equipment, usually for safety testing. So you know, if you've got a piece of equipment that isn't earthed and you're suspicious that it's the chassis is live, if you connect one connection to the chassis, one connection to the live socket of the ball socket with the unit turned on, and press test, you should get a sort of like basically an infinite resistance. There's no connection between the primary of the incoming and the chassis of the unit. So what I'm doing now is I'm applying a DC voltage across this Hunt's capacitor, and it's rated at 400 volts DC. So I'm going to apply 250 volts across it, which is what I'm expecting. Obviously, as everyone should know, that you apply a DC voltage across the capacitor, it shouldn't pass any current at all, and if it does, it will show us up as a resistance. So I'm going to apply 250 volts, and we're looking at the meter here, and we should see that the bar graph swings round to the infinity sign. So let's press the test. Okay, you can see it's 7 meg, it's climbing, but that capacitor is leaky, and it's not too bad, but it's certainly enough to bias a high impedance circuit. Something like if it was a grid coupling capacitor, that would cause problems. That's going to upset the whole performance of the radio. It's going to actually and eventually damage the valves, so that capacitor's got to go. And you can more or less be sure that if that capacitor's failed, all the other Hunt's capacitors will be the same as well. You can see it's creeping up slightly, and some of them are better than others, and sometimes they'll actually fail open circuit. Let's try it at 500 volts. Okay, it's slightly above its rating voltage, but see what it does there. Yeah, it's the same sort of thing. It's pretty leaky. I'm just going to do a normal ohms test on it, and you probably find it would go right way round, so you can't always use this meter. I think only goes to 100 ohms, but you can see that it's greater than 100 ohms at low voltage, but when you start to apply voltage, you're leaking 800, 900k. So caps have got to go, as we sort of surmised. So let's start replacing these and see how we get on. Okay, these are caps I plan to replace them with. There's some caps that I got from stuff that was chucked out of work that's obsolete and sort of non-traceable, and basically we don't use. It was designed for our old valve equipment back in the 70s. Now these are good quality capacitors, and they're actually mil spec, so they should be much better. So let's just do a capacitance, let's do a voltage check on these. Now these are 0.1s at 1000 volts, whereas the Hunts are 0.1s at 400. We're just going to do another test just to see. So we're going to do it at 500 volts, and we expect now the meter to go fully round. So let me just bring the meter around a bit so you can see. There you go. There you go. Infinity. So that cap's fine, it's not leaky. So we're going to replace all these capacitors, and then we'll power the thing up again and have a listen. Right, caps changed. Replaced all the 0.1s, as you see here. All these red caps are 0.1s. There are, well, actually most of the caps in this radio are 0.1s. The yellow ones here are also 0.1s. These are some other caps I had lying around. Basically, these capacitors here haven't actually got an awful lot of voltage on them, usually about 40-50 volts. A lot of them are cathode bypass. Some of the yellow caps here have got higher voltage on them, but all these caps are rated to 1 kV, so they should be fine. Top here, and they're not ideal at the moment, but these are 0.01 or 10 nanofarad. They were originally Hunt's 0.01 microfarad at 400 volts. These are 0.01 polyesters at 400 volts. I haven't actually cut the wire back yet, as I've just spotted. I just powered the thing up as well, and it's I haven't done that other lead. I've just got in for dinner and forgot about it. So reconnect that lead up in a moment, and then we'll power it up and we'll have a listen to it and see if we've got any improvement in overall performance. But all the caps I took out were slightly leaky. They would have failed at some point. The only other problem that we might run into is these carbon resistors. They are prone to going high resistance. There's quite a lot of them actually on the unit. that might need checking. I'm really reluctant to start changing these carbon resistors if they're there's nothing wrong with them and they're still functioning okay. There's some down here, you see, these at the bottom of the screen here. They could all be slightly high in resistance. Usually they're 20% as standard, so if they're 20, even 30% out, probably fine. But much more than that, and I wouldn't replace them. So let's get that capacitor soldered in properly, and we'll give it a power up and have a listen. Right, let's solder that capacitor in properly. Just going to sweep through the medium wave band just to see what we can hear, see if there's anything worth listening to. So we're on, I think we're on the medium wave band. I'm not sure this knob's aligned correctly. Yeah, it's medium wave. But the bottom band here, turn the gain down on the actual, it's got a sensitivity adjustment on the front. I've turned that right down.
But really impressive stuff from Hamilton.
You lived in central London. Well, you go in central London, there's a smile plays on your lips.
So it's clearly working pretty well. The sensitivity control, as I say, is turned right down. Let me just show you what I do if I turn that sensitivity control up. It's mounted on the back of the unit. I'm not sure if it's RF gain or IF gain. Let me find the control. I'm going to turn it up. So I actually had it turned right the way down. It makes a set almost over sensitive, almost like it's prone to overloading.
Very hard. You know, I didn't party. When I got divorced the first time and I hadn't done this and I wasn't playing, I had my sort of mid-20s.
So RF performance seems pretty good. It's certainly sensitive set. The next step will be to check the RF alignment, which we were going to do initially, but I thought it'd be better to do it once we've replaced the capacitors that were obviously failing, obviously leaky. So we could, next thing to do is probably just go through some of the bands and just check to see if the alignment's generally in the right place. I don't really want to start adjusting cores on this thing unless it's absolutely necessary, particularly because they use wax to seal them off. You've got to melt the wax, get the core moving, and then they always risk of breaking the cores. And as the radio is working pretty nicely as it is, it's not critical that I get this thing perfectly scale aligned, but it'd be nice to get it sort of somewhere in the ballpark. So let's go through a few RF sweeps and see what we've got. Right, to do the IF alignment, basically what I did was wrap the lead for the signal generator around the first valve in the front end, which is basically the RF amplifier and the frequency changer, the one that takes the local oscillator and the incoming frequency and then creates the IF frequency of 470 kilohertz and is fed into this next valve, which is here. So what I've done is I've just basically feeding in an IF signal straight into this valve and close coupled it here with this lead. I prefer this method simply because if you're actually connecting up to the actual radio itself, there's a chance you could always alter the impedance of the circuit and alter the response. And also, this is a cop out for me because it's easy to do and I have to get underneath. Unfortunately, all the RF tuning sections underneath. So I wanted to get the RF alignment and the IF alignment, sorry, better because it was clearly sort of peaking around 468, and there was sort of some, looks like there was some double peaks. These are our 3 IF transformers. These are the primaries, underneath are the secondaries. I've adjusted the cores. I've done it. It's a bit of a pain. It would have been a bit of a tiresome video because I've got to melt the wax, adjust the core, and then go back to, and then just go through again. So I've done 1, 2 and 3, and underneath 4, 5, 6, peaked it up at 470 kilohertz, and then I come back again and done the primaries again and back at the secondaries just to get the peak. So I want to show you the difference it's made. So if we look at the we're looking at the 2 meters here. This is obviously our signal strength meter, and this is our IF frequency on the Roden Schwartz. So I think that's about the best view you're going to get. So I'm now expecting to see the maximum eye closure at 470 kilohertz. Now this isn't the way they suggest. They suggest putting a vacuum tube voltmeter or a high impedance voltmeter onto the one of the output valves. But then again, it's the same thing. The service manual doesn't actually show you, although the service manual downloaded doesn't show you all the points for test points. It does tell you where it is on the in the setup, but it doesn't actually show you in the service. It was all a bit ambiguous. So I'm doing it this way, and it works fairly well. So let me just show you. We're at 469 kilohertz, and we're looking for a peak on the IF. We're on narrow IF bandwidth. And if you see, if I tune here, it makes no difference at all. Let's turn some signal strength up. Okay, that's better. So you're looking for the watch the magic eye, and if you can watch this frequency counter at the same time, you should see that the maximum closure on that eye is at 470 kilohertz. I'm closing in on 470, so 463, 664. You should see it closing, and it's just peaked there, 470 kilohertz. Okay, now I'll just do that a bit quicker so you can see. You can see there that it's just passing peak at 470 kilohertz. Okay, so our IF is well peaked, much better than it was before. So that's the IF alignment correct, and the next step I can do is to move on to the RF alignment, and we know that if the IF alignment's correct, the RF alignment should be fairly straightforward. So that'll be the next part. Alright, before we start twiddling about with things, I just want to check to see what the general alignment of this radio is like. So we're tuned to medium wave. You select the knobs just off the bottom of the screen. We're at 550 kilohertz. I'm going to inject a 550 kilohertz signal into the tuner. I'm doing that basically by a loop underneath my bench, which I use for sort of injecting into IF stages and things. It works really well. It's just an old back of an old Pi radio that had a loop antenna mounted in the back, on the back of the back of the chassis, and I basically glued that to the bottom of the bench, and I just couple it up to the Roden Schwartz signal generator. So I'm going to go to 550 kilohertz and see what we get. Now you're going to get a bit of parallax error because obviously it's difficult to get the center of the pointer to the center of the camera and be able to see the signal strength as well. Now someone else mentioned that they thought, I think it was Michael Beanie, mentioned that the signal strength meter was a bit unresponsive. That's because basically the RF signal gain's turned up. If I turn that right down, that drops back. I think it's just a little bit too much gain at the moment. So I'm going to tune to 550 kilohertz on the Roden Schwartz. Come out to 550 now. There's 550, and I can hear it's just coming into tune now. And if I adjust my tuning, see it's peaked there, and that's put me slightly off center from the 550 kilohertz mark. So I'm going to go to, let's go to 800 kilohertz. Let's tune to 800 kilohertz. It'll be a bit easier to see now. Okay, it's 800 kilohertz. I'm going to tune to 800 kilohertz. That's 800 kilohertz there, just gone past. So if I tune, okay. Now this strange peak here that seems to be like a, I'm not sure if it's something else being picked up in the workshop, but if I turn the generator off, it's still there, and it's like a harmonic or something. I'm not too sure what that is, but I can't get rid of it. I thought at first it's the IF being unstable, but I've adjusted the IF transformers to try and sort of break the oscillation, and it hasn't made any difference. So I think it's picking up something, a harmonic or something in the workshop, or it's just a harmonic generated from the local oscillator or something. I'm not sure. But we're at 800 kilohertz now, and you can see we're slightly off, but not far, not badly off. So that's good. I'm not going to adjust that. Let's go to 1 meg. Now it's interesting that you see how the distortion of the camera affects the way the pointer looks like it's not straight or not. That's, to me, looks perfectly square. So there we go. Let's try again at 1 meg. Coming up to 1 meg. Okay, it's 1 meg, and you can see, yeah, we're peaking about there. So that's pretty good for a tuner of this sort of age and this sort of performance. I think you wouldn't expect any more than this. It's 1500 megahertz. It's just below the magic high. If I just turn the voltage down slightly, you can see the 1500 kilohertz mark there. Let's try again. Just go to 1500 kilohertz to 13, 14, 15 now. We're at 1500 kilohertz, 1.5 meg. We're slightly off there, so that's a adjustment of the high frequency, the capacitor stage. But generally, it's pretty well aligned. So I'm just going to move on to the shortwave 1 band, and we'll have another look at that. So let's go to shortwave 1. Let's go to 7 meg. Going down to 7 meg. 7 meg now. This is 7 meg now. You hear anything? There it is. So that's pretty good. You know, that's pretty accurate. Let's go to 6 meg. Change the range on the signal generator. Come up to 6 meg now. 6 meg now. Go tune around. Yeah, so we're slightly off to one side, but not badly. We tried at 5. So this is it's getting worse as we get along. As this 5 meg. Yeah, see, it's moving over. So all right, you get the general idea. The tuner is slightly off tune. We need to try and get that adjusted a bit better. So the next stage will be to run through an RF alignment and see if we can pull this in.